Hi, I'd like to have a talk about Newton's laws. Now, previously I've already talked about inertia and Newton's first law, but I'd like to kind of bring all of Newton's laws into one video here. So let's start with inertia and recap on that. So remember that inertia is the tendency of an object to resist a change in motion. That means that whether the object is moving or whether it's standing still, it's going to resist doing anything that is different than what it is already doing. So if it is stationary, it's going to want to stay stationary. And if you go to move it in any way, up, down, left, right, it is going to resist you in doing that. So that's why when you give a push to something, you're going to feel some resistance. The heavier it is, the more resistance, hence it has more inertia. If an object is moving along a straight line path, a straight constant velocity, then it's going to continue moving in that straight constant velocity unless you push it, and it will resist you. So the more massive the object, again, the more it will resist changing that motion. So that brings us to the statement of Newton's first law. This is actually something that Galileo had said, and effectively Newton had just restated it. And this is why it's known as the law of inertia. An object in motion stays in motion, and an object at rest stays at rest unless acted upon by an unbalanced non-zero net force. An unbalanced or non-zero net force, meaning that it's anything except for zero. That essentially means that there must be some sort of net force acting on the object that will cause it to change its motion. Okay? If there's no forces acting on it that are unbalanced, then it will just keep doing whatever it's doing. So let's move on to Newton's second law. So Newton's second law essentially is this equation here. Now, my second bullet point is a little bit more closely aligned with what he had actually said, but effectively it basically is that F is equal to ma. But notice that there is this symbol here. It kind of looks like it's an E, but it is not. It means the sum of. It's the sigma symbol, and it means the sum of all forces. This is the same thing as to say the net force, or the sum of all forces. Sigma F, it is all the same thing. Okay, net force is equal to ma. This is the acceleration that you observe, and that is a very key point that I would like to make. This is the mass of the object times the acceleration of the object that you actually observe, and that would be the net force. That means that you might have a series of forces acting on an object. So this in turn would equal to force number 1 plus or minus force number 2, depending on what's happening. So let's say we just have an object and we apply a force into this direction. I'm going to call that F1. And then we have a force acting in this direction, and I'm going to call that F2. Notice how F1 is larger than F2. So if we were to do some very basic vector addition, I'll just treat the direction to the right to be positive and the direction to the left to be negative. It's totally arbitrary and up to you as to what direction you make positive and negative. And so if this had a value of, let's just say, 10 newtons, and newtons is the unit of force. In fact, I'll go over that in a moment. And let's say that this one is equal to 5 newtons. So then clearly the resultant force, or the net force, the sum of all forces, all the same thing, would be the 10 newtons acting to the right minus the 5 newtons acting to the left, which gives me a positive 5 newtons. So we have 5 newtons of force acting to the right. That would be our net force. So I'm going to draw a red arrow to the right representing our net force. And so it is that 5 newtons that is equal to ma. So ma is equal to 5. Well, let's say, for example, that we have an object that has a mass of, let's just say that it is a mass of 2.5 kilograms. Okay, so it's 2.5 kilograms. Okay, sorry about my writing there. I'm trying to make it small. Let's see if maybe I can pull that out. Maybe that's a little bit better. So 2.5 kilograms is the mass of the object. Okay, no, that's getting worse. Let me rewrite it just for good measure. So 2.5 kilograms, 2.5 2.5 kilograms. Looks a little better. And so what is the acceleration of the object? Well, if 5 newtons is the force, and that's going to equal the 2.5 kilograms times the acceleration, which we have not yet determined, I'm going to divide each side by 2.5. So 5 divided by 2.5 equals 2. And our units for acceleration, of course, are meters per second squared. So the acceleration of the object will be 2 meters per second squared. Now, let's talk about the units for a moment. So if the units for acceleration, let me even erase the A. The units for acceleration, okay, and in fact I'll even put in that this is the 2 meters per second squared. If the units for acceleration are meters per second squared and the units for mass are kilograms, the numbers of 2.5 and 2 go into our calculator, but the units stay. So kilograms times meters per second. Okay, so let me write over here. So kilograms times meters per second squared. Okay, meters per second squared times kilograms. That is our units for force. Okay, so F is equal to MA. And so you should notice that kilograms times meters per second squared is the units for force. However, just because this is a mouthful to say, we instead say that this is the same thing as 1 Newton. So 1 kilogram times 1 meter per second squared is the same thing as 1 Newton of force. Okay, so this 5 newtons of force up here is the same thing as kilograms times meters per second squared. And since this part down here is kilograms, the kilograms will cancel and you're left with the meters per second squared, which is why our units are meters per second squared. Okay, so that's Newton's second law. One very important thing to note about Newton's second law is that if I were to change any of these values, think of how it changes the other values. So generally speaking, what we'll do is we'll say, if M becomes larger, how does that affect A? And when we say that, we typically are assuming that the third thing, the force, the thing that we didn't mention, is going to stay the same. So effectively, the question of if mass becomes larger, what happens to acceleration? That's really the same thing as saying, if mass becomes larger and force stays the same, I'm going to put a bar over the F to represent that it's going to stay the same. If we were to increase mass, in order for force to stay the same, how would acceleration change? Well, it would have to clearly decrease in order to keep the force the same. Think about this. Think of a car. The force, or the engine of the car, will stay the same. As you pack all of your buddies into the car, what's going to happen to the acceleration? It will decrease. And if you're anything like me, when I was a kid and got my first car, it was a little tiny Toyota Corolla, and putting a bunch of people in that car, you would have a very noticeable difference in the acceleration of the car. So if you're anything like me and had a car like that, then you would have noticed that. This is of course the same idea that manufacturers have all the time, but just in reverse. So manufacturers of sports cars will do the exact opposite. They will do everything they can to decrease the mass. They'll use lighter materials and things like that. And as long as you can keep the force relatively the same, then your acceleration will increase. So that's why the tendency of sports cars now is to use smaller engines, but instead put a turbocharger or things like that that will increase the horsepower but decrease the weight. Okay, so this is known as an inverse relationship where one thing goes down and the other goes up, but you should notice that force and acceleration have a direct relationship. So given that mass will stay the same, okay, so we're going to keep mass the same this time, as I apply more force to the gas pedal, right, I apply more force with the engine, then the acceleration will go up. That seems like a pretty obvious thing, and it's a direct relationship. One goes up, the other goes up. Let's move on to Newton's third law. And so with Newton's third law, we will say that for every action, force, and this is a word that I add in and it is important to me, for every action force, there is an equal and opposite reaction force. meaning that I push you and you push me and you can do nothing about it. So every single time that you apply a force onto an object, okay, so let's say that you have your hand, really terrible, ugly hand, but that's okay. So you take your hand, you apply a force to the right onto this object. So we're going to apply a force from your hand onto the object. And you feel that object pushing back on you, right? Remember, it kind of applies a little bit to Newton's first law because it resists moving. And so since that object pushes back on you, it's going to push back on you just as hard in the opposite direction. So the reason why I'm making it a point to use two different colors here is to express that one is the force that is applied onto this object, and the other one is the force being applied back onto the other object. The action-reaction pair, as it's called, acts on different objects. So if I push you, you push me, okay? My force is being applied onto you, your force is being applied onto me. So there's some interesting implications to this, okay? If I wanted to, for example, apply a force onto some piece of fabric, can I apply an incredibly large, infinitely high amount of force onto this material? I can be as strong as anybody in the world, but the only way that I can apply a large force onto it is maybe to put, something, Sandra in between two things. Or the other thing is, how can I apply a super large force onto it? The problem is that I am limited by, I cannot apply a large force onto it unless it can apply a large force onto me. So I can apply a very large force onto the wall because, of course, the wall has the ability to apply a large force onto me. But this, because it has such a small mass, it has a difficult time applying a large force onto me. So here's the only way that I can really do that without any third object coming into play. And that is to do effectively this. That's my best chance at applying a large force onto this fabric. And that's getting it to accelerate at a very high rate. By getting it to accelerate at a very high rate, remember that since F equals ma, this object has a very small mass, but if I can get the acceleration to be large enough, maybe I can make the force reasonably large. And if I can make the force of the fabric large onto me, okay, so we're going to say that the force of the fabric acting on me, I'll put an M for me, is equal to my force, right, the force of me acting on the fabric. Okay, these are equal and opposite. So that is Newton's third law, and you must keep in mind a couple of things. That action-reaction pairs go together and they cannot be separated. You get rid of one, you get rid of the other. And so here's a super common question, and conceptually I hope that you can catch along with me here. So if I have an object that is being hung by a string, okay, I'm going to give you the action force, and I want you to think about what the reaction force is. So I'm going to say that the action force, and I'm going to just say that this is denoted as M. I'm going to say that the action force is the force of gravity acting down, so this is mg. So the action force is the force of gravity acting down, right? What is the reaction force? For every action force, there's an equal and opposite reaction force. So what is the reaction force acting in this system? Let me take that out of here so it's not distracting. Okay, so force of gravity acting down, that is the action force. What is the reaction force? The most common answer is people say that it is the force of the string acting up. That is the reaction force. Equal and opposite. No, it's not. First off, it actually doesn't have to be equal. What if I were pulling up on this string and I pull up with a very large amount of force? I hope you recognize that this object that is hanging up by the string is going to accelerate upwards. So if I were to apply a very large force, the the force of tension would be very large and it would accelerate upwards. There would not be an equal set of forces between the force of tension and gravity. Clearly, this is not an action-reaction pair. It does not abide by Newton's third law. The other issue, too, is that both of these forces are both acting on this object. That is not an action-reaction pair. If the action force is acting on the object here, then the reaction force must be acting on something else somewhere. So, what is the reaction force? So if this is the action force, right? If this is the action force, then what is the reaction force? And there is another object in this system that you need to consider for a moment. And that object is the Earth. Okay, so here you are standing on the Earth, and there is some object that's being hung by a string. mg is acting down, and what you need to recognize is that if there's a force of gravity of the Earth acting on this object, let's just call it a ball, then that means that there's a force of gravity of the ball acting on the Earth. And so there's an equal and opposite force, right, force of gravity, from the ball acting upwards. The ball is actually pulling the Earth up. It really is. It might seem like a very insignificant small force, and relative to the size of the Earth, it is. But that is the action-reaction force. In terms of the string, if I have my hand, okay, so I'm going to bring my hand back in. Okay, so I'm pulling up on the string, so there's a force that my hand is pulling up on the string, and then the string is pulling down on my hand. I can feel that. That is an action-reaction pair. The string is pulling up on the ball pulls down on the string. That is an action-reaction pair. You get rid of one, you get rid of the other. So if one is a force of gravity, then the reaction force has to also be a force of gravity. They're acting on opposite objects. Okay, that is Newton's third law. So let's put them all together. What if we have an example of a car that is just driving along? I'm going to make an ugly car here. Whoop. Okay, so we have a car that's kind of driving along in that direction, and then we have a bug. That's the ugliest bug I've ever made, but we have a bug that's just kind of minding its own business. And so as the car comes in, car comes in and hits the bug, the first thing that goes through the bug's mind is its butt. But then what happens? So we have a series of laws that will apply. We don't have to go in order either. Let's start with Newton's third law. For every action force, there is an equal and opposite reaction force. So the car hits the bug hits the car, and they hit each other with equal forces. So the car will hit the bug just as hard as the bug hits the car. A common misconception is to think that because the bug goes splat and the bug accelerates real fast, that clearly the force of the car must be larger than the force of the bug onto the car. But they are the same. What is different is their accelerations. So let's express it like this. Let me get rid of this here. And let's express it like this. So the force of the car acting on the bug is equal to the force of the bug acting on the car. And I think what I'll do is, just to simplify things, is I'll kind of get rid of one of these subscripts. And underneath, I'm going to do a substitution. I'm going to say that since F equals ma, that the force of the car is equal to the ma of the car. That is the car's acceleration times its mass. And then the force of the bug is equal to the ma of the bug. So that's the mass of the bug times the acceleration of the bug. And so since the car has a very large mass, it will have a very, very small, not even perceivable acceleration. Since the mass of the bug is small, its acceleration will be high. So when you're driving the car and you hit the bug, you don't get thrust forward because the car slowed down, but rather the car had a lot of inertia, Newton's first law. Something that has a lot of inertia has a tendency to resist a change in motion, so the car with lots of inertia resisted a change in motion, and it kept on moving without much of an unbalanced force. The bug, on the other hand, has very little inertia, so it did not resist a change in motion, which is why the car did not slow down. Okay, so we just applied Newton's first law. And we also applied Newton's second law here, right? So this was us applying Newton's second law. So this is us putting all three of Newton's laws together into one shot. Okay. Let's look at air resistance for a moment. So here we have your granny. She's gone skydiving, and so granny is got a force of gravity acting straight down. So she's got a force of gravity acting straight down. Now, what other forces are acting on her? I'm not concerned about the action-reaction pair at the moment. All I'm concerned about the forces that are acting on her. So the force of gravity acts down, and what else acts on her? Well, when she first jumps out of the airplane, there are no other forces acting on her, just gravity. However, as she picks up more and more speed, then the force, and I should switch colors because it's not really working out. So, no, not that one either. Let's try purple. I like that one better. So the force of the air is going to become larger as she picks up speed. And so what happens is as she picks up more and more speed, let's see if it'll let me do this. As she picks up more and more speed, this force becomes larger and larger and larger until these two forces are about the same. So it is at that point in time at which she will no longer accelerate, because now she's in equilibrium, right? The force down is equal to the force up, no longer accelerating. And she'll stay like that until she pulls the cord. And when she pulls the cord, there will suddenly be a lot more surface area, so a lot more air will be caught. And so this force will become crazy large, and she'll slow down because there will be a net force acting up. And as she slows down, this net force, or excuse me, this force of air resistance will decrease and decrease and decrease until these two forces are equal again. And now she's reached a new terminal velocity. When she is at any speed at which she's not going to go any faster, that is known as terminal velocity. And so she's got a new terminal velocity because of the parachute, where she's going to be able to land safely. So air resistance is different than other friction, where air resistance does change dependent on speed and surface area. Regular friction does not depend on those things. And so when you have an object that is on a flat level surface, let's say, and once we get this object moving, it is going to have a force of friction that is going to act in the opposite direction, and that force of friction will not change dependent on speed, which I think is kind of like one of the last points I want to make here. What is friction, and what is kinetic versus static friction? So when we have friction occurring between a box and a surface, what's really happening? Well, if we were to zoom in on that, we would say that the box tries to move relative to the surface below. And microscopically, there's these bumps and grooves of these two surfaces. So when the box is not sliding, this is known as static friction. Okay, static meaning kind of standing still. And so the box, when it tries to move, it has to rise above these ridges that it's kind of settled into. And it's very difficult to do that. So when you first try and push an object to get it moving or sliding, you must try and break it free of static friction. But once you actually get it to break free of static friction, notice how it doesn't have a chance to settle down into those grooves. So once you get an object moving, it wants to stay moving. And that is known as kinetic friction. So kinetic friction has a lower value than static friction does. It basically means that it's easier to keep something moving than it is to get it moving in the first place. And so once it's moving, that friction force will stay the same. No matter how fast it's moving, that friction force will stay the same. Within reason, because heat will change things and things like that. So kinetic versus static. Before we move on from this topic, I would like to address one more issue, and that is, I want a regular circle. That is the friction between a wheel and the road. So if we have this wheel that is rotating, okay, so it's going to rotate in this direction. So if we have a wheel that's rotating, is it as it's moving and as it's rolling along, okay, as it's rolling along and going along this table, I guess I could have, like, you know, put a little something on this that way we can see that it's rolling. I'll put a couple slashes on it and lock it all together. Let's do that. Let's group and lock everything together. Okay, so now you can see that it's rotating. So as this thing rotates and it moves along, it rotates and moves along, rotates and moves along, is it static or kinetic friction? Because it's moving. Well, it's actually static friction, and here's why. Because the point of contact right here between the wheel and the surface, that spot is not sliding, right? If we could zoom in, the contact point is not sliding past one another. Instead, as this thing rolls and moves, it is a different contact point, and that contact point will stay connected until the next contact point meets the surface. And so that's the point of a wheel, is that it's static friction, not kinetic. Unless you were to lock up, right? Unless you were to like lock up the wheels on your car and you just slide to a stop, then it's kinetic friction. And that's bad, because you will stop at a slower rate. That's why you want your wheels to still rotate at least a little bit when you're coming to a stop. That's why cars have what's known as ABS, anti-lock braking systems. So action-reaction pairs I've talked about, and my example was a ball hung by a string. Remember that action-reaction pairs always act on opposite objects. Here's the help with that. Always reverse the wording, okay? The ball acts on the earth acts on the ball, okay? And then here is my last topic that I want to talk about, and that's pressure and terminal velocity. I did talk about that, so I can kind of forego that issue. So pressure, what is pressure? Pressure is force divided by area. So essentially, pressure is why knives work, okay? So if we were to look at the side profile of a knife, okay, if we were to like look at a knife, it clearly comes into a point that we sharpen it, right? So that's sort of like the side profile. And the more we can get this down to a nice point rather than sort of a blunt surface, right? So this would be a dull knife. But if we can get this to, in fact, let me just kind of fill all this in, right? So this is the metal material of the knife blade. And if we are able to kind of shave this down a bit and make it down to a nice point, then what's happening is that all of your force that you push down, all of that force is going to be concentrated into a very small area. And so we can make the pressure high by either making the force large or making the area small. Either one will make pressure large. So it's actually not the force that will cause damage to an object typically. To cause an object to tear or cut, it is not pressure at all. It's not force at all, it's the pressure. Okay? You actually have a very large amount of pressure acting on you from the air around you, but it's the pressure at a single point that does the damage. Okay. By the way, pressure is measured in newtons per meter squared. Okay, newtons per meter squared, and that's the same thing as pascals. The pressure of the air acting around you, I think, is about 101,300 pascals, which is crazy to think about. If you have a 1 meter square area, so try and like think, okay, it's a little over 3 feet by 3 feet. Okay, I have an area square of 1 meter. My desk is probably a little bit bigger than 1 square meter. And then you put 101,300 kilograms in that space. Kilograms. That's more than 2 tons. Okay, that's more than 2,000 pounds. It's like a good sized car. A small car. And you put it into let me think about that. 101,000 kilograms. It's 200,000 pounds. Holy cow. No, I'm way wrong. It's actually way more than that. So you have a massive amount of force being applied into that area, and that is what's pushing on you at all times. Why don't you just implode? Because your cells, it's called turgor pressure, your cells actually push outwards with the same amount of pressure because your cells, each individual cell, is in equilibrium. Okay, so that's the topic of Newton's laws. Make sure you know how to put all 3 of Newton's laws together, and we will talk more about this later. All right, sorry it was a long one, but it's the biggest topic we've got. It's the basics of physics, basically. So remember, Newton actually invented physics, and he invented these 3 laws of nature that we talk about. So with that, you guys have a good one, and I'll talk to you later.